Well, good morning, everybody. Thanks for coming to the mini workshop on the second day. We're going to open up the session on the DA methods. And our first speaker is Fazlul Laskar. And yeah, feel free to come on up. And you've seen there is a small button with this laser that I guess you sweep to the right if it's drifted off onto their monitor in the back. Yeah, or just ask us to point.
Sure. Thank you. Yeah, it's working. Thank you. Good morning, everyone, and welcome to the data assimilation session. So I'm talking about assimilation of gold observations in WACCMX+DART. And so gold, I believe most of you are familiar about. It's in a geostationary orbit. So it is always watching the same portion of the disk all the time. And in this work, in addition to myself, there are wonderful people like Nick here and Michael, Jeff. They have contributed a lot, and their active feedback and suggestions help this work successful. So as I was telling you, gold is in a geostationary orbit. So it watches the American whole sector, the whole disk, over about like more than 18 hours per day. And so it is gold is a spectral imager in the UV wavelengths 132 to 164. And this is one particular 30 minutes image from the day scan. So what it shows on the left is the day side of the disk, and on the right is the night side. So in the night side, we observe the ionosphere, and in the day side, we observe the air glow, or basically thermosphere. And so in the day side, some of the prominent emissions that we get are the N2 LBH emissions, LBH bands, and in the other one is the oxygen 1356. So we can use this to derive a lot of parameters. And one of the things that like in the data assimilation, there are two ways to do it. One, we can use the radiances itself in the assimilation, and also we can use the derived product. So basically in the derived or retrieved product, there are a lot of validation and a lot of algorithm and improvements went onto this, and that's why I'm using directly the retrieved product instead of using the radiances here. And yesterday we were discussing about the gold latency. At the moment, it's 2 weeks, but it is possible to get it with a 20 to 35 minutes latency. So, okay, let's talk about what is the retrieved product that we get from the radiances. So one of them is the T-disk. And it is the disk temperature retrieved from the radiances. And you can see this was a time when there was a minor geomagnetic storm. So high latitude portions were warmer, and there were a lot of other perturbations in the disk. So these temperatures are very dynamic, and they respond very well to a lot of forcing, lower atmosphere, and solar and geomagnetic forcings. So we have used this kind of temperatures to retrieve the neutral densities, and those were also validated using independent satellite observations. So I'm not going into the details of the retrieval of neutral density here, because our aim is to discuss the assimilation. And one of the other product that we get is like O by N2 ratio. So this is one of the example from our recent superstorm. So where we have observed the OBN2 showed a very, very like fascinating feature that I believe our modeling community will have a hard time to reproduce it and explain it. So this came in the GRL, I think, a couple of weeks ago. Okay, for data assimilation, the title suggesting we are using WACCMX and assimilation framework from the DART, Data Assimilation Research Testbed. And this is an example where I'm showing all the lower atmosphere data. We use a lot of data that are used in the MERA. And also the upper atmosphere, here it is only the gold TDs and OBN2. So this red portion here is the represents where the TDs is, but it can be a bit wider also. Here I limited the latitude or the zenith angle coverage here. And the blue ones are the lower atmospheric, all these lower atmospheric data. And in terms of altitude, you can see it covers the whole atmosphere from surface up to the thermosphere. And so these ones are the lower atmospheric meteorological, and these are SABR MLS. And there is the gold, but gold, as you know, gold is not in a single point, but it's a integrated measurement. So we have to take this into account during the data assimilation process. So on a given day, we assimilate roughly about 1.5 million observations, including the lower atmosphere and the thermosphere. And here I am showing an example of assimilation of gold temperature. And this is an actual assimilation, not a synthetic data assimilation. So initially we did a synthetic data assimilation and we checked that the system works fine. And then we did an actual assimilation. And here what I'm showing is RMS errors for about 9 days of assimilation, and RMS errors from 3 different kind of runs. One is specified dynamics WACCMX, which we know provides the best lower atmospheric constraint. But then if we compare that specified dynamics with 2 of the data assimilation runs, one is the DA1 and DA2. The difference between them is DA1 only adjust the temperature, and DA2 adjust the thermosphere plus ionosphere also. So what we see is both the DA runs provides better RMS errors in T-disk compared to the specified dynamics runs. And we also check that with the OBN2. So in the OBN2 here, we did not assimilate OBN2 here. In this case, we assimilated only temperature and checked the improvement in OBN2. So what we found out, OBN2 also gets better if we do a thermosphere plus ionosphere adjustment when we assimilate T-disk. So yeah, so in this particular case, we used this 5th and 6th as a storm time, and that's why the RMS errors were higher during the storm. And this is one particular thing of interest, is the neutral density, where we used an OC, and in this case, OC using T-disk only assimilation. And in this particular case, we see that the difference between the truth and the whole atmosphere, I mean, the lower atmosphere plus gold is closer to 0 compared to truth minus lower atmosphere only assimilation. So this shows that the including gold improves the neutral density here also. And so these are some of the technical details about like how we introduce the perturbation or spread in the ensemble members. So this particular temperature assimilation I was showing in the previous slides, we use the geomagnetic forcing and solar forcing as a perturbing parameters. And what we observed is like, so if we use the same perturbation in the O/N2, we come into several problems. And one of the, in this case, what I'm showing results from O/N2 assimilation, or it is an OC experiment. So in this case, we know the true state, and from the true state, we derive the synthetic data and assimilated the synthetic data. And when we assimilate synthetic data, we come with a lot of artificial features like this one here, both in the analysis and in the forecast. And so this looks like the previous setup that we used does not work with the O/N2. And so it also messes up the temperature in the model, temperature ionosphere also. So it does not work with the O/N2 assimilation. And so this was later we tried different experiment and found out that we have to do some observation thinning and change the localization setup to remove these artificial features. And then we used we had another issue. What is was like the enzymal spread was very small if we use the earlier ones, and the enzymal, the difference between the forecast and the analysis for this green and the red line, they are very small. That means like the assimilation of the data does not improve the model states. So what we found out that the O/N2 does not respond to the solar forcing too much, because that makes sense physically. And also we know that the O/N2 will not respond to the geomagnetic forcing immediately, because it only responds to the high latitude, but the low latitude, its response comes in after 3-4 hours. So it is not like KP forcing that we are using in a 1 hour assimilation is not enough to introduce enough spread in the ensemble members. And so, and the rough idea is that the spread should be closer to the measurement errors, in this case, about 5%, this line here. So to resolve this problem, what we had to do is we introduce additional forcing in the perturbation. And so we already use geomagnetic and solar forcing. So what else we can use? And so for that, we check the sensitivity of the WACCMX to gravity wave forcing changes. And for that, what we tried is like we changed the diffusion in the WACCMX by changing some the Prandtl number, which is inversely proportional to the diffusion. So in this case, we can see that the O/N2 can be changing by about -15 to +15% when we change the gravity wave diffusion or Prandtl number by 1 to 4. And physically, these numbers are possible. And so that's why it is not very unrealistic. It's still realistic, realistic forcing perturbation. So that's why we introduced an additional forcing or perturbation in the members. So all these forcings have a spread, and the spreads are remaining same throughout the assimilation. So what was the result finally then? And so when we did this kind of perturbation using all the 3 different forcing, and ultimately we got the results from the assimilation. Here I'm showing 5 days of RMS errors in O/N2, latitude versus time in UT or in days. And what we can see, remarkable feature is like the middle one, which is whole atmosphere analysis, RMS errors. So this one introduced the gold data, and the lower one is the lower atmosphere only. It does not have a gold data. So you can see clearly the middle one has the smallest RMS errors. And so the improvement compared to the lower atmosphere only assimilation was about 60%. So this shows that so also we have seen here that compared to whole atmosphere forecast, this one is improved, the analysis got improved. So In this case, we have observed that the O by N2 RMS errors are getting better. And then also we checked with the TAC observations. And so this is like TAC from the truth state, and we compared them with the lower atmosphere only assimilation and whole atmosphere assimilation. And you can see clearly lower atmosphere only assimilation has bigger RMS errors. And when we do include the gold observation, it gets smaller. And also the biases has pretty much similar changes or similar improvements. It was about 25% improvement compared to lower atmosphere. And so we still can see there is a significant amount of RMS errors in the low latitude, but we are not very much worried about this because we also have the cosmic observation, TEC observations to improve the ionosphere even better. So with this, I summarize my talk here. We have used synthetic OC and synthetic data, I mean the OC experiment and the real data OSC gold data, and we have seen, we have tested them in WACCMX+DART, and we have seen improvement in the both in the thermosphere and ionosphere. And some of the future efforts that would be like, we want to compare the combined assimilation of the gold TD scan by N2. And we also want to check which one makes bigger impact on the ionosphere and thermosphere line. And ultimate aim is to transfer the knowledge from the WACCMX+DART to JEDI. So with that, I thank you for your attention.
So we do have a time for a question or two. There's one already. Ricardo online has one.
Sorry, I have a little bit of silly question. I think is my own ignorance. So, do I take it that gold observes directly the ratio of O and N2, as you say, O by N2? And is this a direct variable in the model, or is this? Yeah, can you just talk a little bit about this? Because I'm a little bit confused.
Yeah, thanks for the question. So yeah, gold does observe the spectral intensities, and two of the prominent spectral emissions are oxygen 1356 and LBH, nitrogen LBH bands. So we can use these two emissions to derive the O by N2. So it is a retrieved product, it's not a direct product. And regarding the model WACCMX, it is also not a direct product in the WACCMX. So WACCMX, we do have a oxygen profile, atomic oxygen profile, and molecular nitrogen profiles. So we can use them to retrieve the O by N2. So both the cases.
Yeah, no, I'm just curious then why the ratio, assimilate the ratio if you can infer them separately, so you can retrieve.
This is a very interesting question. The problem is like O by N2, you cannot separate O and N2 because that's pretty much depends on the number of the photoelectrons present there. And so it is a complicated, like oxygen, like O by N2 can be increased by only changing the oxygen or only changing the nitrogen. So it is like, it's a complicated, we cannot separate them.
Thank you so much.
And I think Valery had a question online. He was.
Yeah, thank you, Fazlul. Very interesting talk, and congratulations that you do so much achievements trying to simulate both products and highlight the issues in the data simulation. My question about ON2 continuation of Ricardo questions. Have you chance to check with ON2 data against other measurements like time GUI? As I
yes,
you have
so
this differences between two measurements of ON2. So if we, for instance, would like to assimilate GUI also, how we can handle with systematic differences? What's your-
Yeah, that's an interesting one. So this is still under debate, like how we remove the systematic difference between the Gubi and the gold. And so this would be probably discussed. I'm not very expert on this, but what is important is like we can also find out how much is the bias and quantify the bias and introduce the bias in the data assimilation or correct the bias in the before doing the data assimilation. So we do have strategies to go forward on this.
And remind me, please, what's the latest ON2 product is based? Is it basically on the lookup tables of MCs made by?
Yeah, it is from the MC's lookup table, but I'm not very sure how
Okay.
exactly it depends on the lookup table.
Okay, thank you very much. Excellent talk. Thanks.
Sorry, we need to move on, but either, yeah, or talk in the break, sorry about that. So next talk is given by Russell Landry.